I'll solve one or two examples using planar polar coordinates for particles moving in a plane, which will give you some idea as to how to use these coordinates. As my first example of application of planar polar coordinates, let me take a wire that is rotating with a constant angular speed omega in a plane, and let me put a bead here at a distance initially r0 from the center about which the wire is rotating, and I want to know how the position of this wire changes with time, how its velocity changes with time, what is the force that the wire applies on the bead. Obviously, if it is frictionless, there is no force applied in this direction. There is force applied in this direction because the wire forces the bead to move in this way, and I am going to describe the motion using planar polar coordinates. So, right away I see my r direction is going to be this is going to be my phi direction. In general, if wire is making some angle omega t from its initial position, this is going to be the r direction and this is going to be the phi direction. The force in the radial direction is 0, therefore, the component of force in the radial direction I write as 0, and the component of force in theta direction I do not know, but it is non-zero and I wish to calculate this. If I write the acceleration of the particle in planar polar coordinates, it is going to be r double dot minus r phi dot square in r direction plus r phi double dot plus 2 r dot phi dot in phi direction, and as I have just told you, Fr is 0 and this implies r double dot minus r phi dot square is 0, and since I know that the particle is moving with a constant angular speed, so phi dot is a constant which is equal to omega, therefore, the equation becomes r double dot minus r omega square is equal to 0. Similarly, in the theta direction, f theta is going to be equal to m r phi double dot plus 2 r dot phi dot. Since the wire is moving with a constant angular speed, this term is 0 and therefore, I have F phi, that is the force that the wire applies in phi direction, to be equal to m 2 r dot phi dot. To start solving the equation, let me go back to the earlier equation r double dot minus r omega square is equal to 0. You can see by inspection that this has two solutions, e raised to omega t or r is equal to e raised to minus omega t, and therefore, the general solution r is going to be a, where a is a constant, e raised to omega t, plus b, where b is another constant, minus omega t. This is how r is going to change as a function of time. The constants a and b are fixed by the initial condition. So, the solution r as a function of time is a, e raised to omega t plus b, e raised to minus omega t, and if I am given that at t equal to 0, the particle is at some initial position r0, and at t equal to 0, suppose it was not moving in r direction, so that r dot was equal to 0, then I have, writing these quantities from this equation at t equal to 0, a plus b is equal to r0, and if I take the derivative, omega a minus b is equal to 0. And these two equations give me A is equal to r 0 over 2 and B is equal to r 0 over 2, and therefore, the general solution R t for a particle on a wire that is rotating at a constant angular speed, and the particle is started from a distance r equal to r 0 with no initial radial speed, is r 0 divided by 2 e raised to omega t plus e raised to minus omega t. You can see r increases exponentially, r increases very fast with time. How about the velocity in radial direction? Is going to be equal to r naught omega divided by 2 e raised to omega t minus e raised to minus omega t. General velocity v is going to be r dot r plus r in phi direction, and you can substitute the values and find the general velocity. How about the acceleration of the particle? The acceleration, as you have already calculated, is 0 in r direction and 2 r dot phi dot in the phi direction. Using the expression for r derived earlier, this comes out to be 2 r 0 omega by 2 e raised to omega t minus e raised to minus omega t times omega, which is the value of phi dot in phi direction. This 2 cancels and the acceleration therefore is r naught omega square e raised to omega t minus e raised to minus omega t in phi direction. This is the general expression for the acceleration for this bead moving on the wire. How about the force? The force applied by the wire is given by m a and is therefore equal to m r naught omega square e raised to omega t minus e raised to minus omega t in phi direction. So, you see that we have solved this problem in planar polar coordinates in a simple manner. I would urge you that you try solving the same problem using x and y coordinates. Just to give you an idea, when the wire is moving, wire is applying a force like this, which is going to have a component in x direction, which is going to have a component in y direction, and therefore, the equations you will end up writing would be m x double dot is equal to f x, which is going to be the component of the force in this direction, m y double dot is going to be equal to f y, which is this component, and solve these with respect to time. F changes with time, x changes with time. The solution is going to be slightly more complicated. So, in such situations, use of planar polar coordinates help us. Also, once I get the general solution, an interesting situation is when I ask, say recall this is e raised to I omega t plus b e raised to minus omega t. I am going to ask, can I start the bead from a distance r 0 and give it a velocity in this direction, so that the bead never moves out, it keeps on moving in. Okay, this is just an interesting application of this solution. So, what I am asking is, what should r naught at t is equal to 0 be, so that r dot is always less than 0, that is r keeps on decreasing. Let us see that. So, I am given that r at 0, which is going to be a plus b, is equal to r 0. I have already calculated r dot, and at 0 this is going to be omega a minus b, and I want to have velocity going in. So, minus V0, I want to find that V0 with which I push the particle in so that it keeps on moving in. So, I want to find that velocity. All right. So, what I want is that such A and B so that the particle keeps moving in. This is my equation number 1. Equation number 2 becomes A minus B is equal to minus V0 over omega. This is my equation number 2, and this gives me A is equal to R0 minus V0 over omega divided by 2, and B is equal to R0 plus V0 over omega divided by 2. So, my solution is going to be R0 minus V0 over omega divided by 2 e raised to omega t plus R0 plus V0 over omega divided by 2 e raised to minus omega t, and therefore, R dot as a function of time is going to be R0 omega minus V0 divided by 2 e raised to omega t minus R0 omega plus V0 divided by 2 e raised to minus omega t. This term is already negative, and if I want the velocity to remain negative, that means I want R dot t, which is equal to R0 omega minus V0 over 2 e raised to omega t minus R0 omega plus V0 divided by 2 e raised to minus omega t less than 0. This implies R naught omega minus V0 should always remain less than 0, or V0 should remain R0 omega. So, as another example of this, what we have shown is that depending on the initial condition, if I choose my velocity of pushing the particle in so that it is greater than R0 omega, the particle would keep on moving in. As another example of the application of planar polar coordinates, let me take a particle which is moving circularly on a table. Here is the particle of mass m. It is tied with a thread, and thread is passing through a hole in the middle of the table, and I am pulling this thread or string in with a constant speed v. Again, since the motion is circular, it helps to use planar polar coordinates. So, the position of the particle at any time is given as r is equal to r unit vector r, as velocity r dot is equal to r dot r plus r phi dot phi. R dot is given to be constant and r is decreasing. So, it is some minus v, and therefore, the velocity r dot is equal to minus v r plus r phi dot phi. I want to find the subsequent motion, how phi dot changes with time, how r changes with time, what is the force F needed to pull this thread down. Obviously, the particle is moving in this circle, and therefore, there is, and the table is frictionless, there is no force in phi direction. So, let us go back to what the acceleration of the particle is. It is r double dot minus r phi dot square in r direction plus r phi double dot plus 2 r dot phi dot in phi direction. The force that I am pulling it in with is in radial direction, therefore, that is equal to m r double dot minus r phi dot square, and since it is being pulled in with constant speed, that is r dot is equal to v and r double dot therefore is equal to 0. I have Fr is equal to minus m r phi dot square. Also, r is going to be its initial r0 minus Vt, because r just keeps on decreasing at a constant rate. On the other hand, since there is no frictional force, there is no force in phi direction, and therefore, I am going to have F phi, which is equal to m a phi, which is equal to m r phi double dot plus 2 r dot phi dot is equal to 0. So, r phi dot double dot plus 2 r dot phi dot is equal to 0. I can easily integrate this equation if I multiply this whole thing by r. So, that I get r square phi dot plus 2 r dot phi dot is equal to 0, and you can easily see this is nothing but derivative of this is phi double dot r square phi dot. First term gives you r square phi double dot, second term gives you 2 r dot, and this is equal to 0, and therefore, r square phi dot is constant. Since the derivative of r square phi dot is 0, and therefore, r square phi dot is a constant. So, if the initial position was r0 and its initial angular speed was omega 0, this remains fixed. As I already told you, r changes according to r0 minus Vt square phi dot, therefore, is going to be equal to r0 square omega 0. And therefore, the angular speed, if I am pulling the wire end with a constant speed, is going to change as r0 square omega 0 over r0 minus Vt square. So, we have obtained how the angular speed of the wire changes. How about the force needed to pull the wire in? That, as I told you earlier, is Fr, which is equal to m r double dot minus r phi dot square. R double dot is 0 because I am pulling the wire in with constant speed, and therefore, this is going to be equal to r minus r phi dot square is nothing but r0 square omega 0 over r square, and I square it, which is going to be equal to minus r0 square omega 0 r0 raised to 4 omega 0 square over r cubed, and therefore, the force needed to pull it in is equal to m minus r0 raised to 4 omega square omega 0 square over r0 minus Vt cubed. So, as time increases, this quantity becomes smaller and smaller, and force that you need to pull the wire in with constant speed keeps on going up. So, with these two examples, I have shown you how to use planar polar coordinates. In one case, where there was a bead on a wire and the wire was moving with some speed omega, so this was omega t, the force was in phi direction. In the other case, where we are pulling a mass n, the force is in radial direction. In this case, we can solve for f phi. In this case, we solve for Fr. In this case, I also got r square phi dot to be a constant, and you would recall from your previous courses in your 12th grade that this is nothing but a statement of conservation of angular momentum. In this case, the force is radial, and therefore, the conservation of angular momentum takes place.